Hi everyone, my name is Nagy Wasif, and today we're going to talk about infrared temperature measurements and the correction program. If you're familiar with the process of infrared measurement, you'll notice that sometimes we get different temperatures with two different instruments or two different technicians. And what we're trying to do here is understand where those differences come from and how we can apply them to where we get consistent and accurate results. Now let's take a look at some questions. So the purpose of these questions is to help you identify as we're going through these slides whether or not these infrared temperature algorithms will be beneficial for your fired heaters and reformers. First question you want to ask yourself is, do we even have an infrared program? Right? So correcting infrared is meaningless if there is no infrared readings that need to be corrected. And we'll talk about briefly why an infrared program is recommended versus just depending on thermocouples. The next question we want to ask ourselves is, do we have any integrity concerns with any of our fired heaters, right? So if there's any fired heaters that are of any concern, having an accurate representation of the temperature is greatly going to improve and help us understand how that heater is operating by knowing the accurate temperatures that we're seeing. Not only is that helpful, but it's also going to help us in assessing the remaining life of that tube more accurately. The next question we want to ask ourselves is, what about extending run times? Is there any benefit for us extending the run times of the heater, or do we have scheduled planned shutdowns regardless of how well the heater is performing? So if it is something that would benefit, then these algorithms would be helpful as well. And lastly, this is probably the most important question I would say, is are you seeing significant temperature differences between infrared temperatures and thermocouples? If you are seeing these temperature differences, then these correction algorithms will definitely help us see why you're seeing that significant difference and help us understand which temperatures we should trust. This is what I'm going to cover today. There's a lot more detail that we could go into on each of these points. For the purpose of this presentation, however, I'm not going to go into too much details. However, at the end of this slides, I do have my contact information. If anyone has any further questions, they could reach out to me and I'd be happy to answer. So why infrared? Why not just depend on thermocouples? I mean, we do all have thermocouples in our heaters for the most part, so why not just rely on those? After all, most of the decisions operators make are based on these thermocouple decisions. Well, as you can see, the main reason why we don't want to just depend on thermocouple and why we would like to apply an infrared program is for the simple fact thermocouples might miss something critical. Here we have an example of a thermocouple that was reading 1230 degrees approximately, but what we see is there were hot spots that were missing from those temperature readings, and the operator had decided they're going to go off of the thermocouple readings. So what we notice is there could be potential higher temperature readings, and that's why it's important or recommended to include an infrared program with an infrared camera or a pyrometer, as long as it's a consistent program that could identify hotspots that thermocouples can't identify. If you're not familiar with infrared readings, since we might look at other images, this is the temperature scale. Here we have what's hot, so it's going to be whiter color or brighter, and it's going to be correlated to that temperature versus something of a cooler color, which is going to be a lower reading. So that's going forward, that's going to be the scale you would want to look at versus what's in the images. Infrared is a great tool, not just for knowing what the temperatures are or reading the temperatures, but just a good tool to diagnose the different issues that you could see in a fired heater, right? Whether it's internal coke or poor heat distribution, flame impingement as we see, and then in reformers, catalyst settling. We see these issues clearly identified with an infrared camera, where else we wouldn't be able to see it with our naked eye. So why do we care so much about temperatures? Well, according to the Integrity Operating Windows, or API 584, there are certain parameters that we have to monitor to ensure tube integrity. One of those, which is a key parameter, is the tube metal temperature. Now, infrared camera or infrared inspections are key tools for monitoring the performance and reliability of the fired heater because they help us understand the tube metal temperature. And what we're trying to say is we want to be operating in this safe zone here where you see the green. So we want to be operating in this zone. We don't want to operate below and above. And by understanding the temperature and different kinds of parameters, we'll be able to operate into this green zone here. Now, what we do with the infrared camera is we'll look around and make sure every tube is operating at the same temperature or operating within this green zone. And that's what you get with an infrared inspection that you don't get with thermocouples. Now, if you're looking at this image and you're sitting next to someone, there's two possibilities, as far as I know, of what you're interpreting this image to look like. Some of you are going to look and see straight away, which is what I always thought of, is it's a duck, and here's the beak, and here's the back of the head, and here's the eyes. But then some of you are going to look at this slightly different and say, actually, it's a rabbit. Here's the eyes, but these are ears, and here's the mouth. Now, this is an art form, and it's not something that there's right answer or wrong answer to. But then when we apply the same exact art to infrared, we ask ourselves, well, what temperature do you see here? So to give you a background on what we're looking at, there were two technicians that had their own instrument, their own infrared camera, same infrared camera model to be exact. They shot the same heater on the same day at around the same time, and these are uncorrected results. But as you can see, we're getting very different temperatures. And you have to ask yourself as an operator, if you're getting two different reports from two different infrared personnel with these temperatures, let's just say these were the corrected temperatures, well, which one do you believe is the correct temperature as the operator? Do you assume the safe assumption and say, hey, let's be conservative and say we're firing the higher temperature and reduce our rates? Or do you say, you know what, this guy seems like he has more experience, we could actually increase rates? You're left with a decision, and it's not an easy or straightforward decision. In fact, that decision could be very critical depending on which temperature you decide to choose. We also see that the temperature difference is almost a human temperature difference. So it's not a simple 5 degrees off. But I think based on this example, we do have to find something to where we have to agree to agree. We do need some sort of proven methodology, a way where we could get repeatable and accurate temperatures, and the process is doable by any technician using any infrared instrument. And this is where we started thinking of our algorithm. But in order to understand why we saw these temperature differences, we have to go back to basics. And to go back to basics, that is going to take us through the theory of infrared and how infrared works. So over here, what we see is what we call the black body spectrum, and all our cameras and instruments are calibrated to this black body. Now, this is just a theorized body, but what it tells us is these are the colors we could see with our naked eyes, and infrared, which is anything past the color red, is what we see with these infrared instruments. Now, a big misconception is infrared measures temperature, but it actually measures the radiation that is emitted from the tube. Now, what exactly is the radiation? Well, assume someone walks in wearing a color suit this orange. There's two comments that people are going to probably say, that suit is intense, or that suit is bright. Someone listening might say that suit is hideous, but that's what radiation is, right? It's the amount of brightness or intensity that the tubes are emitting, and that's what the instruments are measuring. And based on what wavelength camera or instrument you use, we correlate that with the amount the tube is radiating, and that's how we're able to get a temperature. These are the two popular wavelengths that cameras are used for inside fired heaters, and the reason those two are the popular ones is because at those two wavelengths, the flue gas is minimized. Now, this is all theory here. In real life, why we don't get accurate temperatures? Because we do run into some issues. As you can see just by looking at this image, we are going to be shooting through flames, which means the amount of total radiation that we get from the camera is going to be affected by the flame patterns and the flue gas patterns. We're also getting reflection from the back wall. We're seeing different angles that we're shooting. So all these factors, plus more that we'll mention, are going to affect the amount of radiation that comes back to the camera or the instrument. And that is why we don't get consistent results between two technicians or two infrared cameras because of different issues that we run into. So it's said that infrared is a lot like magazines. It has a lot of issues. And a lot of these issues are what we found out to be environmental and instrumental. The main issue we'll discuss today is going to be the size of source effect and how it affects not just each camera, but each lens of each camera, and how the heater geometry can affect how we get the true tube metal temperature readings. Now, one thing I do want to mention, in order for us to get true, repeatable, and accurate results, all of these factors need to be accounted for, not just a few that we're going to discuss today. But let's go ahead and look at the heater geometry and how that affects the true tube metal temperature. So with conventional IR, technician or operator would come with the infrared camera, look at the heater and say, so this is a reformer example, looking from a helicopter or top planar view. And we're looking and we're seeing these are the tubes, and here's the different wall readings. And what we're seeing is we're taking temperatures, and you can see this background temperature is 1500 degrees. Now, suppose this operator sets his camera as 1500 degrees for background and 1 emissivity for all of the tubes. Now, that's fine, and that's going to give you a temperature correction, but is it accurate? Because what we're trying to say by doing this is this background is going to affect not only all these tubes, but all of these tubes. But in real life, what we found out to be is all these backgrounds are actually slightly different. So for us to apply the appropriate corrections, we actually have to be able to incorporate the background temperatures that affect the tubes most appropriately. So in this case, for example, we would want to apply this background instead of this background, and so on. And for these set of tubes, we would want to take these backgrounds into consideration and these backgrounds, but not just the back wall temperatures. We actually want to take different kinds of temperatures. So over here, we'll take the ceiling temperatures, the back wall, the tunnel roof, the floor. So we want to take as much background temperatures as possible. And by doing so, what we're trying to say is all these background temperatures are going to reflect on the tubes, and they should be taken into consideration. So that's why we want to build the geometry in order to understand how the background affects the tubes. And one thing to emphasize is we're actually taking a weighted background average, not just any background average. So it is weighted, and based on where the tubes are, they're going to be affected heavily on which background is closest to them. The other issue we said we'll talk about today is the size of source effect and how it affects the tube readings. So when an operator takes an infrared image, what they're essentially trying to get is the tube temperature or that radiation as we discussed earlier. And as you can see with the color scale and the temperature readings, here are what the tubes are reading, and they're trying to get that temperature reading. But unfortunately, some of that radiation in the image actually leaks out of the image. And even though that temperature is a good temperature, it never actually makes it to the instrument. But simultaneously, outside of the image, where you're going to see the flame patterns or the flue gas or the background temperature, which is going to be hotter than the tube metal temperature, that is actually going to leak into the image, and it's going to appear to be coming from the target tube. So in essence, what you're seeing is you're going to believe a temperature that's much higher than the actual tube metal temperature. Again, this is just for the size of source effect, not taking into account all the other errors, the instrumental and environmental errors. The reason why this is a significant error is because when you have design temperature and you go above the design temperature, every 20 degrees above design temperature that you increase your temperatures, you're cutting your creep life in half, which means if these are the true temperatures and you believe these two temperatures, and let's just say the design temperature is 1200 degrees, so at 1195, you actually have over 100 years left of creep life. But if you believe the 1300 is your true tube metal temperature, well, now you only have 3.5 years left of creep life. Size of source effect not only does it affect your camera, but it affects each lens of each camera. So each camera needs to be calibrated along with each lens for that specific camera. It is, however, negligible when using a pyrometer. And that's something you could see in the field when you take a pyrometer and measure your temperature with a pyrometer versus with an infrared camera at that same location. You could see a significant difference. And that difference is due to the size of source effect. So these correction algorithms help in various ways. The main one obviously is catastrophic failures. You'd hate for something to happen just because of a faulty temperature reading. It helps assess remaining life more accurately, and you prevent unplanned outages. And again, we discussed earlier integrity operating windows. You want to be operating within those, and you want to have that confidence where you're operating. So let's look at a few case studies of how we use this technology, and we were able to apply these algorithms to correct these temperatures of the two images I showed earlier. So again, these are the two images. Again, they're taken by two different technicians with different instruments. Now, this is actually considered an ideal image. So if there's any two spots that would yield similar temperatures, it would be these two locations. And the reason why those two locations would be ideal is because the temperatures in these images are isothermal, where the spot is located at least. The line of sight, you're not shooting through a lot of flame, so these spots are relatively close to where the sight door would be. And the angle of incidence. So the angle of incidence we didn't talk about much earlier, but if you're watching TV, you kind of want to be sitting in front of the TV. You don't really hear parents complaining, my kid is always sitting at the side of the TV, right? And the reason is they are always sitting in front of the TV. Because just like light, infrared is best when it's seen in a perpendicular pattern. Whenever you get to a 40-degree angle or less, then that starts affecting your temperature reading, and emissivity for those surfaces will need to change in order to apply a proper correction. But these are considered ideal images, and after we applied all the correction algorithms of all the different instrument and environmental factors, these were the temperatures that we were able to see. So you could see the main difference between the two temperatures was actually due to the size of source effect. So both instruments had completely different size of source effects, but we went down from 100-degree difference to about a 10-degree difference. And just like the title of this presentation, we literally changed infrared 180 degrees by applying these algorithms. Now, one thing I do want to point out is going to be the skin thermocouple. And the skin thermocouple is actually reading lower than what it should be because it was shielded. So if the operator was trusting this temperature, he was actually trusting a temperature that was also erroneous. But over here with cameras, you could see we're really getting similar results. With conventional way, when we did it initially, we were getting about 50 or 70-degree difference. But with all the algorithms that we applied properly, we're getting a 10-degree difference. These are what we call the total uncertainty with these algorithms. Because we take all the instrument factors and environmental factors into account, we could actually calculate exactly what the uncertainty is. So it's a plus or minus error, although we do believe this is the most likely temperature. But there is an uncertainty of 40 degrees in this case and about 40 degrees in that case. With the skin thermocouple, there is no uncertainty that we could quantify, and that's a big difference between the infrared cameras and the skin thermocouples. So one thing I do want to point out is a lot of times when we talk to operators and they believe their thermocouple is reading accurately or their conventional IR, there's no issues with it. And that could be true. But I do want to point out one thing, corrected temperatures don't necessarily mean you reduce the temperature reading from the raw temperature to the corrected temperature. Sometimes you actually correct the temperature by increasing the temperature. So there's times where when we don't correct the temperatures, it's reading lower than what we get after we correct the temperatures. In this case, we were reading 1,000 degrees and the corrected temperature ended up being 50 degrees higher than what we were seeing initially in the field. So sometimes we do have that false sense of confidence where we believe the true tube metal temperature is one thing and thinking that we're conservative by being below the actual design temperature versus after applying all the correction algorithms, we might actually have to increase that temperature reading from what it actually is. And I put this picture up because it would be similar to a guy speeding and telling the cop, I'm sorry, I thought I was going 70, and he finds out his pedometer was broken. He also has that false sense of confidence. So that's one reason why we like to apply that correction algorithm. When do most people go to the doctor? When do most people take their car to a mechanic? The answer is usually whenever they need to, right? But I think we'd all agree if people went to the doctor more often and if people took their car to the mechanic for regular checkups and maintenance, their car will probably last longer and they'd probably be healthier. And that same is true for fired heaters. A lot of times we think if it ain't broke, don't fix it, which is true for most of us, but a lot of times there is an opportunity there where if we did go and we did do several other inspections, we'd be able to have a better performing heater. And we'll look at this example in a reformer to where we were called, and the problem with this reformer is there was an issue, and that issue they were worried about was creep damage. So they thought they were firing really hot and they were worried about having to reduce the rates. So we looked at their temperatures and we said, hey, you know what, we have these algorithms that might be able to help, and they were very interested because they really didn't want to reduce the rates, as you can imagine. We flew out, we looked at their technicians and saw the way they were operating their infrared camera, and we trained them on how to take measurements properly as far as eliminating some of the environmental and user errors as well as instrument errors. So we trained them on the different aspects of placing spots on the tubes. We calibrated their camera for the size of source effect, and then we corrected their temperature readings. And by doing all that, after we were done, they continued operating at their current production. And more importantly, they had no creep damage concerns. So you could see the temperatures went down significantly. Their max temperature went down nearly 100 degrees, and their average temperature readings went down approximately 75 degrees. So in summary, what we did to get these corrected values was we went and applied all these corrections from our algorithms in order to get these corrected results. As you can see with conventional IR, there's really two factors that we correct for. With Quest Integrity's algorithm corrections, we're not only able to correct all of these, but even nowadays with restrictions with Corona, now that technicians can't just travel anywhere they want and do the same jobs they used to do, similar to what I used to do back when I first started with Quest, we're able to do is actually train any technician using any camera, whether it's on-site or virtually, to be able to do the work and get consistent results. So by doing so, you don't have to depend on a certain technician or a certain camera. Sometimes the cameras need to be fixed. Nowadays, you can't travel to certain cities because of the COVID restrictions. So we could actually apply all of this technology and algorithms virtually. It doesn't have to be in person. These are just the sources I used. These are very skilled and professional people I came across our career. This book here by Dr. Peter Saunders is where we got our algorithms from, and those are what we apply in our correction algorithms. So we base it off the scientific study that he did and wrote in this book. And it's a great book for anyone who is working or would like to learn more about infrared. And again, he was instrumental in the decisions that we made in the science that goes behind the infrared corrections. So since we don't have time for questions and answers, but I do get these questions often, I wanted to go ahead and run through some frequent questions that we get and try to answer those. But also, I do want to point out that my contact information is also here and at the last slide in case you come up with questions that we don't address during this FAQ section. So the first question, did the clients find the Quest Integrity infrared correction algorithms beneficial? Short answer is yes, they did. And on average, we did see a return on investment of 700%. Now, that doesn't mean we're going to have such a return on investment for every single person that decides they want to use these algorithms, but those discovery questions that were asked in the beginning help us determine what the return on investment is. And a lot of clients have said these algorithms change the way they do practice and how they operate their heaters. The second question, does the size of source effect affect the flare camera calibration? The answer is no. It actually doesn't do anything to the camera. All we do is we'll send the camera to New Zealand to a laboratory to be calibrated for size of source effect. Keep in mind, we'll send not just the camera, but all the lenses that need to be calibrated with the camera as well. And we just get a calibration curve. And once we apply those corrections to the instrument, we get a size of source effect correction. Now that size of source effect correction, all it is are just constants that we have to take into account based on the flare calibration. Now, if you have to send your camera back to flare to calibrate it or do some maintenance work, then you'll have to send the camera back to New Zealand to the laboratory to be able to get a more appropriate or an updated calibration curve for the size of source effect. Here is another question, and it's mainly a misconception. Are thermocouples more accurate at reading temperatures than infrared measurements? No, they're not. In theory, thermocouples are easier to look at the temperature at a glance, and they're better at real time because they're always continuously there and the heater doors are closed. However, thermocouples, as we saw in the presentation, could be falsely relied on, but also it really depends how both of these are applied. So whether the thermocouple is applied properly or infrared is applied properly, they should actually both scientifically be reading the same temperature rather than one is more accurate than the other. Unfortunately, because of the way conventional IR is, most operators and engineers base their operation off of thermocouples rather than infrared measurements. The last question asks, my tubes are scaled. Is there any way to figure out the true tube metal temperature using these algorithms? So infrared measures the surface of the tubes. It doesn't measure the true tube metal temperature necessarily. It just measures what it sees. And if there's scale present on top of the tubes, then that's what's emitting and that's what the infrared camera or instrument will read. Fortunately, what we are able to do is apply an advanced engineering technique, which is based off of API 530 Annex B. And what it does is we see in this image, there's scale on this tube, and we believe this is where the spot that's going to yield us the true accurate temperature. And as you can see, this is what the true tube metal temperature should be. But when we put the spot on the scale, we end up adding scale thickness temperature, which increases it by 48 degrees. And then we actually have some tube fouling that increases the temperature by another 45 degrees. In the end, what we're left with is a tube metal temperature of 819 degrees after correction. So you could see this difference between what the actual Tmax is versus what the corrected scale tube is. It's about 100 degrees. So what we do with the Annex B is we're actually able to correct temperatures that are on scale. In essence, we're able to provide a final temperature of 726 degrees. And last thing is, I do want to thank you all for your time. It was a pleasure speaking here. Fortunately, I didn't get to see all your faces, but if you do have any questions or comments or want to hear more, please don't hesitate to contact me anytime. My phone does go silent in the middle of the night, so I might not be able to pick up, but I will get back to you as soon as possible. Thank you all so much and have a wonderful and safe day.